tissues and organs and tumors, actually. Not for human transplantation right now, because that's still some time away, but as model systems. The problem in medicine now is the drug development pipeline. And one of the reasons why drugs cost so much money, $2.6 billion to get one drug to market, is because there's a lot of drugs that don't get there that fail on the way, and those costs need to be accounted for. And so what my group and many other researchers believe is one of the problems is the models that we've been working with to test drugs before we go to humans are they're not good enough. For example, animal models and two-dimensional tissue culture dishes or petri dishes, these are not humans, which results in drugs failing when you do bring them to humans. So what our group is trying to do is to develop what we call organoids, or really small engineered organs and tissues, to implement those as preclinical models, which then will drive the price down, allowing more drugs to succeed, but also the ones that fail will fail earlier, saving everyone a lot of money. Here we go. So what my lab works with is several enabling technologies that allow us to build these models and keep them alive and have them functioning as they do in the human body. So we use 3D bioprinting, bioreactor machines, and microfluidic devices, which are little machines that allow fluid to be handled between different channels and chambers inside of which our models live. Let me give a little example about why the systems we build are always in 3 dimensions. Nothing in the body is in 2 dimensions, first of all. We live in a 3-dimensional world. So let's use cancer as an example. So these cells on the screen are highly malignant colorectal tumor cells that came from a patient, so dangerous cells. What you can see here in the screen are on the left are cells with these green borders, and those borders mean they're anchored together. That means they're not going anywhere. So these highly malignant cells that in a human were actually traveling all over the place and causing patient death, when you put them in 2D, they don't act bad. So that's a problem. They're not malignant in 2D. So we started building tumor models, creating these spheroids, kind of spherical tissues. And so when you move into 3D, as you see on the bottom here, and you put these tumors inside of a surrounding tissue, like a liver, you see these biomarkers or these proteins that indicate whether or not the tumor is dangerous or not dangerous start to switch. They become more malignant. You've turned on expression of proteins that indicate that these cells are now dangerous. So just by moving into 3D, we've now created a model that's much more like the tumor would be inside a human body. Now, most patients die not because of the tumor growing in the primary site, but because the tumor will actually migrate to a different site. Here we see colorectal tumor. Most patients, well, many patients that die from colorectal cancer actually die when it reaches the liver because it's connected by circulation in the body. So we started thinking, well, we can engineer one tumor and one tissue. Can we engineer multiple and put them together and kind of create a miniaturized version of the body? So we built what we call metastasis on a chip. So metastasis is when the tumor cells migrate to a different site. And here you can see a little device that's about the size of a microscope slide, so several inches long, and it has several locations that we actually engineer or bioprint a 3-dimensional tissue in each site. For example, a colon that has a tumor in it, and then a liver that's downstream. These things are connected by flow, and what we see, if we wait a little while, the tumor cells, which here are in red, will actually grow over time, And in the bottom right picture, you can see they've now actually burst out of the colon organoid or tissue that we created, and they've entered sort of this artificial bloodstream. If we wait a little bit longer, we actually see that the tumor reaches the liver, which is a pretty nice tool that we can now start to do drug testing, model the disease, and a variety of things. Now, what we're really excited about, in addition to doing drug testing, is also personalized medicine. So this is a huge effort across the country where a patient will come in, they'll take part of that tumor out, send it off for genetic profiling, and the goal is to identify a mutation in the tumor that we can then prescribe a specific drug that will be more effective for that patient. Now, the problem is when you send out that tumor, you get a list of all these different mutations and all these different drugs. So the oncologist or the surgeon still has to kind of come up with their best guess. So what we want to do with our engineered organoids or tumor organoids is take part of that biopsy, build a personalized model for that one patient, and now we can screen those same drug choices and hopefully come up with a better treatment for that individual patient. So we're working with cancer surgeons and oncologists over at Wake Forest Baptist right now to actually do this. We have a variety of tumor models, not just colorectal and liver, pancreatic, lung, glioblastoma, which is a brain tumor. And we're also building multiple site complex models that don't just have 2 sites, but have even more now. Which brings me to an interesting topic that we've been working in for a few years, which we call a body on a chip, not just a metastasis on a chip. So we've been funded by the military to create a system that has a heart, a liver, a lung, and a blood vessel with the goal of looking at toxicology, biochemical warfare agents, and developing countermeasures, and of course drug screening. So our group has been rather productive, and so we didn't just do 4, we did 6. So we have a liver, a cardiac, a blood vessel, a lung, but we also have testes, colon, and we're able to assemble these things in a modular system of organ chips. And here we see one of these systems where it's kind of organs connected by tubing, kind of a simple way to look at it. And these things interact and stay alive together in the one system. They actually communicate, which I'll get to in just a sec. But to show the utility of this technology, we've started looking at how do drugs that were actually recalled from the market by the FDA for actually killing people. And we started testing these drugs on this system. So here's a list of a whole bunch of them, just a subset of the many drugs that have failed. But these have actually killed people. So when we take our tissue organoids like our liver and our heart, when they're healthy, they appear green using some fluorescent imaging that we have. When the drug starts to kill those cells, they turn red. So we're able to just pick up this signal of cell death within this system using these drugs that were actually recalled for killing patients. So this is a powerful technology. One of the things we're really interested in is this concept of organ integration, and why is that important to link these things together? Well, in the human body, no organ exists in isolation. They actually do communicate. So here's an example of a liver and heart system. I think if you look carefully, you can see this is our heart that actually is beating a little bit. And here you can see our technology that allows us to sort of track the propagation of these beats over time. We did a test with epinephrine, which causes increases in heart rate, and propranolol, which is a beta blocker, which will actually block this effect. Now, liver is supposed to be very good at metabolizing propranolol. It's a first-pass drug. So if our system works, the liver should be able to influence how these drugs work. So on the top here is our baseline beating activity. If you administer epinephrine to a cardiac organoid by itself, it increases by about 150%, or a 50% increase. Now if you add propranolol in the third graph down, it's 100% blocked, you're back to baseline. Now if you add a liver to the system, the liver can now metabolize that propranolol, and you do see an increase when you add the epinephrine. And so you're able to establish these sort of dynamic experiments that you can look at things like side effects, which I'll show next. So we expanded this system to liver, cardiac, and lung. And we wanted to show initially that we could target one and not all of the organs on the system. And so we used a drug called bleomycin, which causes lung inflammation. So we were expecting that we would sort of cause damage in the lung, but not the liver and the heart. We didn't see any lung death, which was weird. And we did, however, see that the cardiac organoid in the group that was treated changed its morphology. So in the bottom right, you can see it's kind of raggedy. They're not really connected together, and it completely stopped beating. So we were kind of confused as to why this had happened. We did control experiments and verified that this drug doesn't do anything to a heart by itself. Absolutely nothing. So here's what our sort of stream of experimentation. Bleomycin gets admitted to the system, causes lung inflammation. Now the lung is able to release all these different proteins into the bloodstream that indicate an inflammatory state. Several of those are interleukin-8, IL-8, IL-1 beta. And so we started querying our system to see if these inflammatory molecules could now be toxic to the heart. And what we saw is, well, indeed, we saw tons of this IL-8 stuff, but we couldn't find any connection that it was having any effect on the heart. So we kept looking. And so we looked at this IL-1 beta, it's there, and it is actually directly cytotoxic to the heart. So we sort of inadvertently stumbled onto a really interesting drug study where we could actually start to look at how a drug might cause something to happen, which then had downstream effects on another organ. It's a side effect. And without having multiple tissues and organs represented in these types of systems, you can't look at side effects. So really the way that the pharmaceutical industry has been doing this in the past just doesn't really cut it. And that might be one of the reasons why so many drugs have passed with flying colors in our early preclinical models and then been pulled from market. So now we're continuing to build on the system, adding more organs, looking at these types of more complicated drug studies, as well as deploying it for the DoD so that they can start looking at countermeasures for chemical and biological warfare agents. So I think we're living a very exciting time for science where the engineering that we're doing can really have an effect on medicine